So this is our Chapter 11 lecture. Chapter 11 is on liquid, solids, and intermolecular forces. The first major topic is the states of matter. Um, Luckily, you've probably had information on the states of matter in every science class since middle school, I would guess. There's a lot of different components to it, but the big three things to know about the states of matter, comparing and contrasting, is between the shape, volume, and compressibility. So a solid has a fixed shape and a fixed volume. A liquid has the shape of the container but a fixed volume, and a gas fits the size of the container for both shape and volume. Compressibility means able to be made smaller. So since the particles in the solid are as close together as they can be, you cannot compress a solid any farther than what it is. You can compress a liquid and a gas, but since the liquid particles are usually a little bit closer together than the gas, the liquid can't be compressed as much. So if we look at the picture here, other characteristics of each you should know is the density. Density is just how much stuff is in a given area. The movement of the particles and the intermolecular forces between the particles. So you can see here the solid are very close together. It's a very high density. There's little to no movement. The particles just vibrate in place. And there's very strong intermolecular forces happening between the particles. In a liquid, the density is kind of in between. It's in the middle, medium density. The particles can move, but again, they're not as free-flowing as a gas. And then again, there's medium intermolecular forces. A gas has very low density, the particles are free-flowing, and the intermolecular forces are very low. Phase changes are just when you go from one of those three phases, solid to liquid to gas, etc., and so forth. Solids and liquids are what we call condensed phases. Converting a gas into a liquid or a solid requires the molecules to move closer. So this is accomplished by increasing the pressure, cooling down the temperature, anything to get the gas particles to slow down enough that they stick together more. What actually happens is you slow their movement down so that the intermolecular forces are strong enough to hold them together. Converting a solid into a liquid or gas requires the molecules to move apart, which is accomplished by heating or reducing pressure. So this is a great graphic that just summarizes all the different phase changes. So you have the three phases here. The enthalpy, remember, is the energy, which goes up. So if we're going to go from a gas to a liquid, those phase changes are called vaporization or condensation. Solid to a liquid is going to be fusion, which is the other word for melting and freezing. And then gas to solid, sublimation, deposition. So you need to know all those vocab words. This again is another graphic showing you phase changes, but the thing it has here that I wanted you to see is the order part, the entropy part. So gases have total disorder, very high entropy, and then the entropy decreases as you go from a gas to a solid. So when you're talking about phase changes, you should know when you're going from a gas to a liquid to a solid, what happens to the enthalpy and what happens to the entropy. That's important for you to know. Intermolecular forces is the next major topic. Inter means between, molecular for molecules. Intermolecular forces are the attractive force between molecules. It is much weaker than an ionic or covalent bond. So when we're talking about intermolecular force, I like to think of it as a magnetic force. So it's kind of the difference between a magnet and superglue. A bond would be superglue. It's very much stuck together, very hard to take it apart. You can take it apart eventually, but a bond is very, very strong. Whereas an intermolecular force is like a magnet. Things are still sticking together, but it doesn't take a whole lot of force to separate them. Intermolecular forces originate from the interactions between charges, partial charges on atoms or ions. So it's all about something called polarity. So when we're looking here, this is a intermolecular force. Again, here's the bond between the two atoms. The intermolecular force is between the two molecules themselves. So they're two totally different forces. When you melt or boil, so when you're kind of increasing the phase, you're going to get breaking of the intermolecular forces. So that's really, phase changes are all about either strengthening or weakening the intermolecular forces. IMF, just so you know, is the abbreviation for intermolecular force, is formed when a substance condenses. Boiling point reflect intermolecular force strength. The higher the boiling point, the stronger the attractive force is, because the more force it takes to break them apart. There's three types of intermolecular forces. The other name for them is van der Waals forces. Van der Waals and intermolecular forces mean the exact same thing. The three are London dispersion forces, dipole-dipole forces, and hydrogen bonding. And if you look at this list, London dispersion are the weakest, hydrogen is the strongest, and then dipole-dipole are in the middle. An ion dipole force is separate from the van der Waals forces, and that is a force between an ion and a polar molecule, which we'll talk about. So the first one is called a dispersion force. Sometimes it's called dispersion London force. It's present in all molecules and atoms. It results in the fluctuations in the electron distribution within the molecule. Now the key is it's called a temporary dipole. So what happens in a dispersion force is it's usually between non-polar substances, things that don't have that natural magnetic charge. And what happens is when they come close together, when they interact with each other, it causes them to temporarily shift its electrons and become a polar molecule. So it's a very, very brief dipole moment, we call it. It turns into a polar molecule very briefly, and in that instant it sticks together and then it breaks apart. It's a very weak force. The magnetic depends on how easily the electrons can move. Could be the size of the atom, the electron cloud, the electronegativity difference. There's a lot of components to that. So the strength of the dispersion force depends on the distance between the molecules, the polarizability, which is basically the ease with which the electron cloud can be deformed. Remember, a polar molecule is because of an uneven distribution of electrons. The more electrons there are, the more polarizable the element is, and that's just simply, remember, the number of electrons is equal to the atomic number. Also, the molecular weight and the shape of the molecule. The more surface area available, there's a greater dispersion force. So basically, the more magnetic area, the higher the strength will be. Forces between spherical molecules are also smaller than those between cylinder-shaped molecules. So we see here this graphic is showing you dispersion force. It starts out as a non-polar substance, comes into contact with each other, they both form temporary dipoles, and they have an attraction. The next force is a dipole-dipole force. This is present between all polar molecules. This is a permanent dipole. This is when the molecule is polar. Remember, polar is the idea that you have an uneven distribution of an electron, so you have one side that's slightly positive and the other side that's slightly negative. This ends up with a negative and positive pole, which then stick together like a magnet. The polarity of molecules depends on the miscibility of the substances, which is the ability to mix without separating. Polar liquids are only miscible with other polar liquids, and nonpolar are only miscible with other nonpolar. Polar liquids can dissolve both polar and nonpolar solids, but nonpolar liquids can only dissolve nonpolar solids. Hydrogen bonds, again, I don't know why they use the word bond, but they are the strongest type of intermolecular force. And what they are is just a specific type of dipole-dipole force. A hydrogen bond is just a very, very strong dipole-dipole intermolecular force. It only exists between a hydrogen atom and the elements fluorine, oxygen, and nitrogen. So you can think of FON, F-O-N. There's a very large electronegativity difference between these elements, which really makes the electrons move to a great degree to one side, which causes a super dipole. So examples would be HF, NH3, H2O. Anytime you have a hydrogen with a FON, fluorine, oxygen, or nitrogen. This is showing you hydrogen bond. This is in water. And the hydrogen bonding in water really give water a lot of the properties that it has. So for example, why does ice float? Because of hydrogen bonds. So theoretically, ice is made of water, so the density should not be that different. But the molecules in the solid are usually more closely packed, which means the solid is usually more dense. But with water, the ice is ordered with a different structure because of the hydrogen bonding. Therefore, the ice is slightly less dense than the water, so it's going to float. An ion dipole force, remember, is separate from the van der Waals forces. This is between a polar molecule and an ion. For example, Na plus in water. Water is very polar, Na plus is an ion, so they have a very strong intermolecular force. This is responsible for an ionic substance ability to form a compound with water. This is just showing you some examples of that. This is showing you different intermolecular forces. Ion dipoles, the one we talked about. So we have a sodium ion in water, a hydrogen bond, a dipole-dipole, an induced dipole or a dispersion. And then these other two are a little bit different. But really, if you know this one, So 1, 2, 3, 4. You're able to explain. What you're going to do with those intermolecular forces, you're going to explain properties of liquids using the idea of intermolecular forces. So one of the first properties of liquids we're going to talk about is surface tension. If you see the picture real quickly, that's the ability of small things to kind of sit on the film. It's like water almost makes a film with itself. The molecules in a liquid are attracted to their neighbors. The surface molecules are only attracted inward, so you get a liquid that has a sort of skin. Surface tension, that vocab word though, is the amount of energy required to increase the surface area of a liquid. Basically, how much it needs to break that downward pull. As the intermolecular force increases, the surface tension increases. So if we look at this graphic and think of this as a pond, for example, and here are the individual water molecules. They have hydrogen bonding between them. So if we look at these middle molecules, they have forces surrounding them 360 degrees. They're going all over the place. But at the very surface of the liquid, there is a downward pull on the surface molecules, but there is no upward pull to counteract that. So what happens is the overall force is pulling it down. This is why water beads. And this is why bugs, and if you can do it a paperclip, can actually sit on top of the water. You can see it almost looks like it's bending. That is due to surface tension. Viscosity is the resistance to flow. Whenever you think of viscosity, you usually think of syrup, like for waffles or pancakes. A liquid and a gas flows by sliding molecules over one another. So if you have very high intermolecular forces, they're not going to slide as easily. So when something's highly viscous, it means it does not flow easily. So as the intermolecular forces increase, the viscosity increases. As the temperature increases, the viscosity decreases. Everyone knows that because when you heat up oil or you heat up syrup, you're going to get a more flowy liquid. Capillary action is the ability of water or liquids to rise up very narrow tubes. This has to do with the xylem and phloem in plants and how the water goes up the roots, etc. This is due to adhesive and cohesive forces. So this picture right here is showing you viscosity. You can see this liquid flows very easily and the viscosity is going up as you go to this one that's actually hardly moving at all. Cohesive versus adhesive forces. Cohesive means that the substance is very attracted to itself. Adhesive means it's very attracted to something else. Couple ways you can remember that. Cohesive, kind of like cohabitate, it wants to stay with itself. Adhesive, you can kind of think of like adding two separate things. So if the adhesive forces are higher than the cohesive forces, if it wants to stick to a surface more than itself, you're going to get an upward U-shaped meniscus. If the cohesive are greater than the adhesive, if it likes itself more than something else, the liquids are going to be a downward meniscus. So the best two examples is water and mercury. Water is going to have a concave meniscus because it's more attracted to the glass. Mercury is going to have the opposite because it's more attracted to itself. So you can actually see it. The water is going to hold on to the side of the glass. The mercury is going to kind of move away from the glass. Again, just showing you a little bit easier to see. The water again is going to be, it's more attracted to the glass than itself. The mercury is more attracted to itself. Phase changes or changes of state. We kind of went over these at the beginning. So this is just, again, a summary of the phase changes you should know. Again, with phase changes, it's important now not to understand not only what's happening to the molecules, but to understand it in terms of energy and disorder. Any energy changes that accompany phase changes are state changes, which we talked about again. Delta H is the change in enthalpy, remember. Melting is endothermic, vaporization is endothermic, and sublimation is endothermic. Kind of if you want to think you're going down, some reason that helps you remember, melting you're going from a solid to a liquid, vaporization you're going to a liquid to a gas. Those are all endothermic processes. Deposition, condensation, and freezing are all exothermic. In general, it takes more energy to completely separate the molecule than to partially separate it. And this is showing you the sequences down here of endothermic and exothermic reactions. Some molecules on the surface of a liquid have enough energy to escape. This is called vaporize or vapor pressure. This is kind of like the whack-a-mole idea, is as some other things are trying to escape, they're kind of hit with the molecules that have already escaped. As the number of molecules in the gas phase increases, some of the gas molecules strike the surface, and as that happens, the vapor pressure actually makes the boiling point go down. So as the temperature rises, particle motion increases, so the number of collisions increase. After some time, the gas becomes constant and reaches a state of dynamic equilibrium. We're going to talk about this a lot. Um, Dynamic means moving. Equilibrium is when, if you think about osmosis, that's the classic one. Um, we're going to have movement of particles, but dynamic equilibrium means the total movement is equal. It doesn't stop moving. It's not like particle motion stops, it just becomes equal. You're going to have simultaneous equal rates. In this case, in terms of dynamic vapor pressure, it's the point when as many molecules are escaping the surface as striking the surface. Vapor pressure is the pressure exerted when the liquid and vapor are in a dynamic equilibrium. This is called equilibrium vapor pressure. So we look at the picture, we have water molecules that have vaporized. Some of them are hitting the surface of the liquid, others are trying to escape. This is just showing you the vapor pressure is how you would measure it. So we have the ethanol here escaping, and we're using a manometer to measure that vapor pressure. If equilibrium is never established, the vapor continues to form, and eventually the liquid will evaporate to dryness. That just means it all goes away. That's called volatility. So I know volatile, it sounds like it's, when something explodes, but it's not. Volatile just means it's able to evaporate. Things like alcohol and those kind of things are very volatile, evaporate very quickly. The higher the temperature, the higher the kinetic energy, the faster the liquid evaporates. This is just showing you the fraction of molecules to enter the gas phase. It's all about collisions. Liquids boil when the external pressure at the liquid surface is equal to the vapor pressure. This is called normal boiling point. Whenever you hear normal, it means at sea level or 1 atmosphere. The temperature of the boiling point increases as the external pressure increases. There's two ways to get a liquid to boil. You can increase the temperature or decrease the pressure. A heating curve is a plot that shows heat versus time. So during a phase change, adding heat causes no temperature change. The energy is used to break the intermolecular forces rather than actually raise the temperature. These points are used to calculate the enthalpy of fusion and the enthalpy of vaporization. Supercooling is when a liquid cools below its freezing point and still remains a liquid. So this is a heating curve. Heating is just when the temperature is going up. Cooling would just be when it's going down. If you look, you're going to have these increasing parts, and then you're going to have the solid straight parts. The parts where it's increasing is obviously where the temperature is going up. This is where it's in the phase. So where you see these points right here, this is where it is solid. This is where it is liquid. This is where it is a gas. The horizontal lines are where it's actually changing phase because the energy is not moving. It's going to break the intermolecular forces. So we have solid, 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 melting. Liquid, 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 boiling. Gas, gas, gas. So you can see here it's going to be time on the X, temperature on the Y. So you're going to be able to see how long it takes for something to boil. Other facts you can get from this is boiling point, melting point, because that's where these straight lines are. You can also do specific heat equations with this because you can find temperature changes. So you're seeing like the heat here, you can see Q equals MC delta T. This is talking about the change that happens between this point and this point. Gases may be liquefied by increasing the pressure at a suitable temperature. So critical temperature and pressure is basically the highest point at which a substance can exist as a liquid. Basically, the temperature and the pressure get so high that it can't be a liquid anymore. It's always going to be a gas. These are just some critical temperatures and pressures of some substances. This would not be something that you would have to memorize. It would be something you were given. The Clausius-Clapeyron equation is the idea that the vapor pressure of a liquid increases with increasing temp. This relationship is not linear. The relationship is exponential. Most likely you will not need to use this equation, but I think it's good for you to have it. Notice it has a constant B that depends on the type of gas. You can use to calculate slope and to find 2 points, kind of like x1 minus y1, etc. and so forth. A phase diagram is pressure versus temperature. So really the biggest difference, heating and cooling curve is temperature versus time. Phase diagram is pressure versus temperature. It's going to show you the temperature and pressure in which phases exist and where phase changes occur. It's always going to have the same general idea. The one all the way to the left is going to be solid. The middle pie piece looking one is going to be the liquid. And the vapor is going to be all the way to the right. And on this line, these lines here are where the phase change occurs. So if you want to find the normal freezing point, remember normal is one pressure, you would just find one atmosphere, find the point on the line, and then go down and find the temperature. So you're going to see regions that represent conditions where that substance is a solid, liquid, and gas. You're going to see lines which represent the phase changes. The triple point, which is right here, is where all three lines intersect, all three phases intersect. It's where a substance has the ability to exist in any phase. It's not in all three phases at once, it just can be in any three. And then critical point up here is the pressure or temperature at which, remember, above which a substance can no longer be a liquid. Again, just a bigger picture of a phase diagram, and you can see phase diagrams are different for different substances. So we have a CO2 versus a water. The structure of solids are different, which give the solid different properties. So a crystalline solid, when you think of crystal, you think of like a gemstone, like a diamond or a ruby, which is where you have well-ordered, definite arrangement of molecules. The intermolecular forces are similar in strength, so they tend to melt at specific temperatures. This is like a quartz, diamond, salt, sugar, whenever you think of any kind of crystal structure. An amorphous solids, when there's no orderly arrangement, rubber, glass, anything that you can make curved is most likely an amorphous solid, because a crystalline structure you cannot curve. You're always going to have a straight edge. The amorphous solids have intermolecular forces that vary in strength, so they melt over a range of temperatures. A unit cell is the smallest repeating unit of a crystal. This is what makes up the crystal lattice. You have different types of cubic unit cells. Easiest way, I think, is to see the picture of them. You're going to see all of them are going to be at least simple. They're going to have the corners represented. So that's the blue here. So a simple is just when all you have is the corner. Body center is when you have the corner and then you have an atom directly in the center. Face center is when you have the corners and then it's like a cross in the middle. So there's, if you see here, you can see it's in the middle of these. There is no one in the center. And then base center is just when it's on the top and bottom. Crystalline solids have structures that maximize the attractive forces between the particles. The particles can be represented by spheres, and you can see how the molecular crystals are packed or stacked on each other. Basically, they're going to be, in most crystals, are going to be as stacked and as close to each other as they can get. There are two choices for the third layer of spheres, the hexagonal close packing or the cubic close packing. Again, this is not very likely to show up on the AP exam, but it's good to go ahead and read about it. What you can look at here is the coordination number, which is the number of spheres directly surrounding the central sphere. The physical properties of the crystalline solid depend on the attractive forces between the particles and the arrangement of the particles. There are 4 types of solids. Their properties are summarized here. So we have molecular solids, metallic solids, ionic solids, and covalent network solids. You can see the intermolecular forces that exist, the structural units, melting point, and some other properties, conductivity, and some examples. Molecular solids consist of atoms held together by weak IMFs. They're usually soft, they're often gases, poor conductors. Covalent network solids have atoms that have a lot of chains, long chains. They have higher melting points because of stronger covalent bonds. Ionic solids obviously have things together held together by ionic bonds. They're very hard, brittle, high melting point. They have a high electrostatic force of attraction. And this, how strongly they're held, really depends on the charge of the ions. Metallic solids are basically metals. It's the whole idea of the sea of valence electrons. They're very ductile and malleable. They're going to have these metallic solids that have the hexagonal close packing, the face-centered cubic molecules. Sea of valence electrons is how metals bond. In metals, the bonding is too strong to be explained by London dispersion forces, but there are not enough electrons for covalent bonds. What happens is all the metal nuclei float in a sea of delocalized valence electrons. All the electrons are shared by all the atoms. It's kind of like a waterbed. This is what gives metals a lot of their properties, like conductivity, malleability, ductility. This is a picture just showing that. So you have the metal here, you have the nuclei here, and then all the electrons, you can see they're not really directly connected to a nuclei. They're all kind of spread throughout. And that is our Chapter 11 lecture.